So there was some confusion concerning the mark with the rat DNA, okay, which is put on. And if you say, oh, look at this, I mean, the band pattern corresponding to what we had in the other footprint is a little bit different. It means, oh, how hard do you digest this? I mean, if you add more DNAs, one, you get smaller bands. But the important part is that you get a regularly spaced pattern. And from this, I mean, you can start thinking about the nature of this DNA you got from this Martian organism. So, what do you believe? You just got this probe back from Mars. You've been waiting for this for 10 years. This is your Nature paper. So, but we need a conclusion. So what does it look like? Should that be more bacterial kind of DNA, or should it be more eukaryotic style DNA? You want a Nature paper, right? So, yes?
I think the smears kind of indicate that it can be degraded everywhere. So
basically what's said here is that when you have these smears, and the more nucleus you add, the more you get until you get this minimal size around the 50 base pair where DNA one may not really like it anymore. So if you have like spacing, absence of spacing, it indicates that there are no regular structures organizing the DNA, that nucleus. So that will be the conclusion. Alternatively, they should have different sizes. So instead of like one species, you have like a population of species doing the same trick. But that seems to be a very unlikely scenario. Does that make sense? So the conclusion would basically be because there are no regular spacing. So it cannot be corresponding to eukaryotes. But of course, you cannot rule out that there are some proteins there because, as I said, well, DNA with no proteins on would be very odd. Good. Any questions for this? Then we'll jump on to the next level, the chromatin scaffold. So again, here we have this certain animal fiber that we wrap it up to. But then I mean that's a little compensation. I mean, what really matters here is when you hook it up to this protein scaffold. So we actually have very big protein scaffolds in the nuclei that are organizing the DNA, and I think I should have a picture of this. So when you look at a chromosome, then deep buried within the whole structure, you actually have a protein skeleton in here to support the DNA material that you can use as anchor points for attaching DNA. And there's an important feature to this, because that means you can actually start organizing your DNA in loops, like this. Alright? So that means that people have actually been sitting here and said, look, here's my picture. I don't know how clean this is for you. It may be difficult here. We can actually visualize the DNA strands here, like the certain animated fibers. You can actually track them and start, doing like the kind of maze thing and following around. And you can actually see that you have loops that are returning back to the same starting point. So the DNA is organized in loops. Now, why is that actually interesting? This is actually interesting because now you can start putting in DNA structures here of the same type, so that you can say, oh, this is a loop which is closed for transcription. This is one that is active for transcription. And we talked about DNA 2' isomerases already, and we talked about superhelicity a little bit, I think. Didn't we? No, maybe it's in another class. But does everybody know what a DNA 2' isomerase is? Nobody does. So when you have DNA, then DNA is typically underwound. So what does that mean? It means that if you take a DNA helix and wrap it around and you don't do anything, it's neutral. However, if you start twisting the helix a little bit and close it again, then you'll have DNA which is underwound. So what's the good news about this? That means if you have a plasmid, so the plasmids that you're getting when you make an E. coli preparation, how many did an E. coli preparation of DNA in the lab, in the course? Some? Very little? Okay. But if you purify DNA, then it would typically look like a big knot here, and it would move fast in the gel. Now, if you actually nick the DNA, then it will open up in a structure like this. Okay? Because the liquid will act as a swivel, and then this can move out. Now, what's the reason to have the DNA like this? So let's just put it up. So if I take this DNA which is underwound and forcefully put it on the table so that it's making the ring, which is possible, then I'm going to lose base pairing. For the vast majority of the plasma, open up. So if you have negatively supercoiled DNA, then you flatten it down, then you'll see this. So that means that you actually have, when you have a negative supercoiled DNA which is a little bit more dynamic and then easy to open up, which is good news for transcription factors, helicases, and this kind of stuff. So most DNA which is actively in use is underwound and negatively supercoiled. And in order to get something that is supercoiled, it needs to be a closed circuit. And to remember, DNA chromosomes and nucleus are linear. Okay? So you cannot supercoil anything if it's linear, because then it's just twisting around. But if you hook it up like this, in circular domains, then you can have a system like this. Is this understandable? So this is one feature. We look for other features where this is come into play. This is just it, and then you can start to build up structures of this, and it gets more and more complicated with this type of structures. And I mean, it's not really super understood how this is going on. But there are some proteins that are isolated, has to do with this, and those are these SMC proteins, small maintenance chromosomes that are acting as ring structures. You can intuitively understand how that can act in a condensing reaction, because it's ring structures that can open and close, and when they're open you can put in fibers, and when you're putting the fibers you can close them again so they'll stay together. You can do this either this way, or you could really think about it in this perspective. But again, this is processes that are quite poorly understood. I think I'll just skip to this. And then finally, you can get into something like this, which is out of the scope that we'll talk about today. Now, when it starts to get more interesting from the topic of today is when we get into the interface, where we have the majority of the transcription. Basically, the reason I have this is that if you have a chromosome like with this structure, you can again easily convince yourself of that if your transcription factor, well, then it's difficult to find a way to this structure and bind a specific sequence. Whereas it's opened up in interface, this is where we have most of the action. Now, what actually happens to the chromosomes when we open up the structures and go from this very compacted to those that are more open? That means bead on a string and 30 nanometer fiber. So what happens to the DNA? Well, what happens to the DNA is that it's not just scattering around so that one chromosome will fit in the entire nucleus, because in principle it could, but it's rather restricted to areas. So here we have chromosome 8 stain. You can see this is a part, this is a diploid cell. So that is a chromosome from the father, this is from the mother. So these two chromosomes are located in two different places in the cell, but they sort of, have sort of similar space. So that's it. So you open up the chromosomes, they don't distribute all over the entire nucleus, but rather fills out a certain domain. And the two homologs, if you're diploid, are not located in the same places. And you can see a more complete picture here, but the conclusion will be the same. Any questions for this? Alright, so now we're getting into the exciting part here. Where I say, oh, look at this. We can actually start to control whether we should be in the bead of the string, or we should be in this 30 nanometer fiber, or compacted form. As we call it, heterochromatin for compacted, open U chromatin. Now, in the context of these loops, this also gets into place, because now here's something we could play on. Say, this loop needs to be heterochromatin, but the neighboring loop, that's the one we have to have active. Those genes in this particular loop should be active in that particular organelle or organ, and then we can control it in this way. So we'll keep this in mind, that these boundary zones could have something to do with regulating what is active and what is not. Okay, so that's setting the stage for what we're going to dig into after the break. So that was an appetizer of the next two lectures. Any questions for this? Then break until 10.